Hello, in this recording I'm going to discuss the concept of spin. So in the previous recordings I've talked a lot about angular momentum, which is a property of objects in motion, in particular executing rotational motion. One example is an atom in which we have a positively charged nucleus and an electron circulating around of it. This would be orbital motion, which generates orbital angular momentum. We describe that with a quantum number L. Now the type of rotational motion which obeys exactly the same laws would be a molecule, for example a hydrogen molecule with two nuclei, which is rotating in space. In this case this would be molecular rotational motion. And this is also quantized and is described by an angular momentum quantum number which is usually called J. Now we've seen that the L quantum number can take values 0, 1, 2 and so on, and similarly for a rotating molecule the J quantum number can also take values 0, 1, 2. And these quantum numbers, the L value for the orbital angular momentum of an electron in an atom and the J value for the molecular rotation, does depend on the rotational state of the molecule, how fast it's rotating or how fast the electron is going around the nucleus. So we know, for example, that L is 0, the electron is in an s orbital, L is 1, an electron is in a p orbital, L is 2, an electron is in a d orbital, and so on. And the electron can have any one of these states depending on its state of motion. We've also seen the mathematics for the angular momentum, that it's described by operators Lx, Ly and Lz, and they have cyclic commutation relationships, and that each of the operators Lx, Ly and Lz commute with the total square angular momentum operator, and that we can define angular momentum eigenstates, which are eigenstates of the Lz operator with eigenvalue h bar ml, and simultaneously eigenstates of the L squared operator, where the quantum number ml takes values from plus L down in steps of 1 to minus L, so that's 2L plus 1 values altogether. So we always get an odd number of ml values. We've seen that the energy levels of an atom or a molecule split in a magnetic field, and the number of levels which are generated is as given by these numbers of 2L plus 1. It turns out, though, that to explain the spectra of atoms and molecules, these concepts were insufficient, and two graduate students in Holland called Uhlenbeck and Goudsmit proposed, in order to explain some experimental observations, that the electron has a half-integer angular momentum quantum number. Initially that was thought to be impossible. It can be shown that half-integer angular momentum is not compatible with motion, physical motion. But later it turned out that this concept was correct, and there's another type of angular momentum which is displayed by fundamental particles, but not by macroscopic objects. And this type of angular momentum is now called spin, and it's intrinsic angular momentum. It does not derive from the motion of the particle, but is part of its intrinsic nature, like mass or charge. And it turns out that almost every particle in nature has spin, and in diagrams we often denote it by drawing an arrow on top of the particle. Now fortunately the mathematics of spin are identical to the mathematics already developed for ordinary angular momentum. So we have spin operators, which for an electron are usually denoted using small s, and they obey the same commutation relationships as the L operators. And we can define spin eigenstates, which depend on a spin quantum number, small s, and the magnetic quantum number m sub s. But the mathematical rules for these states are exactly the same as already discussed for the case of motional angular momentum. The main difference is that the value of the spin, s, does not depend on the motion of the particle, but on the nature of the particle. So s is intrinsic to the particle, and each particle in nature has its own value of s. So for example, for the electron we have s is 1/2. For the proton, similarly, s is 1/2. for the neutron is also a spin half particle. And the only one we come across in chemistry which doesn't have spin 1/2 is the photon, the particle of light, which has spin 1. Spin 1 of the photon is responsible for phenomena associated with polarization of light. So whenever we use polarized sunglasses or something, we are exploiting the spin of the photon. The spin of the photon is also responsible for selection rules in atomic spectroscopy. If we draw out an energy level diagram of an atom, the lowest level is 1s, and then we may have 2s, 2p, and so on. The symbols SPD, these refer to the orbital angular momentum quantum number L. So S means L is 0, P means L is 1, and D means L is 2. Now, when light is absorbed or emitted, a selection rule is that the value of L has to either increase or decrease by 1 unit. Light, it can induce a transition from an s orbital to a p orbital, or from a p orbital to a d orbital, or from a p orbital to an s orbital. But one can never go from an s orbital to an s orbital. And the reason for that is simple if one considers the spin of the photon. The photon has spin 1, so when it's absorbed by an atom, that angular momentum has to go somewhere. So if the atom is in an s orbital to start with, it doesn't have any angular momentum. So it then acquires the angular momentum of the photon, which is spin 1, and therefore generates a new state which has angular momentum 1, in other words a p orbital. Similarly, the angular momentum L equals 1 for a p orbital may cancel out the angular momentum coming in from the photon, and then the p orbital can then make a transition to an s orbital, or it can pick up another unit of angular momentum to make a transition to a d orbital. So these selection rules in atomic spectroscopy are due to the spin of the photon. The orbital angular momentum quantum number L must change by plus or minus 1. So let's look at the properties of the electron spin. The properties of the spin operators are essentially identical to the properties of rotational or orbital angular momentum. It's simply though that the spin quantum number is 1/2 for an electron. We say that the electron has spin 1/2. And that means that the ms value can take one of two values, either plus 1/2 or minus 1/2. The plus 1/2 eigenstate, which we could write as follows, where the half here means the value of the spin quantum number, and the plus 1/2 is the magnetic quantum number. This we usually write as the state alpha, and we call this spin up. And the state with ms is minus 1/2 is often written as beta for brevity. So again, these two numbers in the ket here, the first one, the half, is just the spin of the electron, which is 1/2. And the minus 1/2 here in the second place, this is the ms value. So this state, the beta state, is often called spin down. And these states obey the rules we would expect for angular momentum. So the sz operator, when acting on the state alpha, generates again the state alpha. It's an eigenstate of the sz operator, multiplied by the eigenvalue h bar times the ms quantum number, which is plus 1/2 for the state alpha. So the eigenvalue is plus 1/2 h bar. Similarly for the state beta, this is also an eigenstate of the sz operator, and this time with eigenvalue minus 1/2 h bar. And similarly for the s squared operator, the eigenvalue in this case is h bar squared times the angular momentum quantum number, which is 1/2, and then the angular momentum quantum number plus 1, which in this case then would be 3/4 h bar squared. And the same goes for the beta state. And we can form the matrix representations of the angular momentum operators again in just the same way as was done for ordinary angular momentum. So for example for the operator sz, since we have two spin states, this can be written as a 2x2 matrix. So we can calculate the matrix elements of the sz matrix in the same way as was done for ordinary angular momentum. So for example this element in the bottom right hand corner can be calculated as the bracket between the beta bra state the SZ operator, and the beta ket state. The SZ operator, when applied to the beta ket, generates the beta ket back again, but multiplied by the eigenvalue, which for the beta state is minus 1/2 h bar. And we can put that expression together. The minus 1/2 h bar factor comes out, and I get the bracket of beta with itself. And since the states are orthonormal, this is just 1. So the whole matrix element is minus 1/2 h bar. And if I repeat such arguments for all the elements of the matrix, then I deduce the matrix representation of the SZ operator as being 1/2 h bar with the ms values 1/2 h bar and minus 1/2 h bar on the diagonal and 0 off the diagonal. Similarly, I can form the S plus operator by adding the Sx operator with I times the Sy operator, and it can also be represented as a 2x2 matrix. The element we're looking at there is the bracket between the alpha state, the S plus operator, and the beta state. And we can examine the action of S plus on the state beta. This uses exactly the same rules as for the orbital angular momentum. The S plus operator lifts the ms value, which is minus 1/2, up to plus 1/2. So I get the state alpha. So the raising operator there, the S plus operator, has raised the ms value from minus 1/2 to plus 1/2. And we can deduce the complicated factor using exactly the same calculation as done for orbital angular momentum. And the complicated factor is given by S times S plus 1, where S is 1/2, minus the old value of ms, which was minus 1/2, multiplied by the new value of ms, which is 1/2, square rooted. You can write that out explicitly. That's h bar 1/2 times 1/2 plus 1, that's 3/4, minus 1/4. And that makes 3/4 plus 1/4, which is 1. So the whole expression evaluates to h bar times the bracket between the bra state alpha and the new ket state, which is also alpha, and therefore the term evaluates to h bar. So the matrix for the raising operator for spin half is simply given by h bar times a 2x2 matrix with 1 in the top right position and 0 everywhere else, as one can verify by explicit calculation, multiplied by h bar. And similarly, the matrix for the lowering operator, we can form the matrices for the x and y operators. The Sx operator is given by 1/2 of the sum of S plus and S minus. So it's given by 1/2 h bar and then a matrix. And similarly, the Sy matrix is given by 1/2I times the difference between the two shift operator matrices. So it's given by 1/2I h bar and a matrix of the following form. The Sz matrix, which we had before, is given by 1/2 h bar and this time a matrix with 1 and minus 1 on the diagonal. And it's easy to verify, it's just by multiplying out the 2x2 matrices, the essential commutation relationships, that the commutator of Sx and Sy is given by IH bar Sz, and repeating for the cyclic permutations. Okay, so that was the essential mathematics of spin, in particular spin half, for the electron. In the next recording, I want to discuss how angular momenta are combined.